Good morning, students. I guess Professor Ron's happy that we have some nice cool weather, but I don't like the cool weather when it rains, so we're going to get a little bit of that too. But again, that's where we live. But hopefully the cool weather helps you to get better rest. I know growing up in North Carolina, I was always happy for the colder months because it made it easier to get better rest in the evening, and that's really important right now. Let me just remind you that we'll have our last quiz this week. We'll be completing the work for the course, the lecture material, and we will have a lecture next week, only one lecture, and that'll probably be attributed to just doing some review. I've got a practice final that I posted, and I will post some solutions to that also. That would be just a way to give you a way to refresh all of the knowledge that you have in the class. We've covered quite a bit of material. And then, of course, our final will fall next week between Tuesday and Thursday, the same time frame, the testing window that I've offered for all of the exams will be offered for the final exam. So just keep that in mind as you're starting to plan. I will, of course, send out an email probably today giving you more information about the final exam. And also, just remember as you use your computers, we often leave our computers on. We don't refresh them. Um, Often defragmenting can occur with your software. And so it's important to often, close your browser, refresh your browser, restart your computer just to give it a fighting chance. I do that every day, and I also make sure to check settings to clear cache so that you have plenty of memory to do your work. Sometimes your computer can get very slow if you don't do that. And you all are children of the computer. You're probably very aware of this, but I'm just letting you know I don't have an issue with it anymore, but not growing up with the computer in my face, I have to think about these things. So if you've noticed some issues with your computers, please take opportunities to restart them and refresh them. That will certainly make life easier. Now, also, let's see, those are all the announcements that I have. I'm glad you're here today. I want to take some time today to talk about polar coordinates. Polar coordinates will be studied more in Calculus 3 when you start doing double and triple integrals. You will also study cylindrical and spherical coordinate systems in Calculus 3, which will again be very useful and very uh, germane to doing problems in physics and engineering. So polar coordinates will just be basically a subset of that, and I think you will actually enjoy this discussion. So let me go ahead and share my screen. Now, when it comes to polar coordinates, we just basically want to start out with a few preliminaries and then do several examples. But I also want to make you aware in your ebook, you have a really nice uh, summary, so to speak. These are special polar graphs. We'll talk about these during this lecture. And what they do is just summarize the types of polar graphs that you will come in contact with in calculus and other courses. And this is a very nice summary. It gives certain particular equations and how you can actually look for certain characteristics based upon the equation. This is a really, really nice tool. And so what I would recommend is that you go ahead and print this out. And as you test, this can basically be a reference sheet. I don't, again, it's like having the list of famous infinite series when you work with power series. Uh, you use things often and remember them, but when you've got plenty of things on your plate, it's nice to have a good reference tool. So you can find this in your ebook. The ebook is a great source of examples, just like the PowerPoints. And in addition to my lectures and lecture notes. So take advantage of all this good information that you have. But I like this particular sheet. It's really good. Now, for the polar coordinates, let's just go ahead and define what we're talking about. You may have even seen this before, so I may be telling you things that you know about. If not, again, we're starting from scratch. So polar coordinates. Now, first, we're going to have a directed distance. And basically, when we refer to a coordinate description in polar coordinates, it will be written this way. That is, we're going to have an r and a theta. So that will be the order that we use in polar coordinates. And that's really important. Again, this is convention. It's just like the conic sections. How can we do conic sections without conventions? And as many of you that will be future engineers, there are many mathematical conventions in engineering that everybody uses. And if you want to communicate with another engineer, you have to use those conventions. Otherwise, you'll be speaking a different language. So the first thing is R is a directed distance. It can be plus and minus. Is a directed distance measured from the pole or the origin. We're going to call the origin of the Cartesian coordinate system and the polar system the pole. So normally we call this the origin, okay? Now, when I say directed, and this is important, R can be positive and it can be negative. In certain coordinate systems, you don't have this flexibility. So this is going to remind you a lot of the unit circle in trigonometry. 2, theta is an angular distance, just like you did in trigonometry, hard to say early in the morning, an angular distance measured from the positive polar axis. Now, again, the polar axis, if you think in terms of Cartesian, will just be the positive x-axis. We can always go back to Cartesian. WebAssign will sometimes do a polar coordinate system where you mark off 0, pi over 2, pi, etc. Sometimes they'll write it in Cartesian, but you can go back and forth between the two to kind of give yourself some reference points. So this will be the positive x-axis. And we'll draw some pictures too. Now, what do we think about theta? You know, we're thinking about theta as supplying some type of direction for R. And it's going to be the same that you used in trigonometry. So now theta will be positive and correspond to counterclockwise measurement, just like S1. And when I say S1, I mean the unit circle, counterclockwise measurement. And then, of course, if theta is less than 0, just like we've done before, this will correspond to clockwise measurement. Many times when we do our polar graphs, we'll start with the Cartesian graph and mainly focus on the positive values of theta, clockwise measurement. So this is just like S1. So we'll just say same convention as unit circle. So that's good to know. That's like I said before, this will remind you quite a bit of the study that you did with trigonometry. And 4, we've got a couple of identities that support modulo 2 pi on the unit circle. So for instance, if we take the coordinate pair r theta, then you can certainly add any integer multiple to theta and still get an equivalent angle due to the modulo 2 pi of the unit circle. So we could say r, and then I'll just use k. We use this in pre-cal, where k is an integer. Some students like to use n, but WebAssign in pre-cal that I teach, you use k. So I tell them, I said, be sure to follow formatting so WebAssign will recognize what you're doing. Now, what we're going to do when we have an r, an additive inverse, basically what that's going to mean is going to be like a vector. For instance, when you think of a vector, just say a plain old vector v like this. The convention is to define the additive inverse of v as being the vector in the opposite direction. That is, we make this convention when we talk about vectors. We've got the same magnitude, but when we actually apply the additive inverse, that reverses the direction of the vector. And so again, when we think of a coordinate representation of a vector, this makes perfect sense. And again, what's nice about all of these coordinate systems is that conventions are set up so that they are consistent. Okay, now, how do we interpret the additive inverse with the polar coordinates? Well, we'll have to do this. So if we have a negative r theta, this is basically reflection through the origin. So that means that we have to add that multiple of pi to do that reversal of direction, like the 180 degrees. So this will be r and then theta plus an odd multiple of pi. So we'll say 2k plus 1. And normally we just think of, in this case, k being 0 and just adding the multiple of pi to give us that reversal of direction. So this particular identity ties into the convention for standard vectors. And then again, thinking about coordinate representations. So when you think just in general here, we draw what appears to be just the standard coordinate Cartesian system, the coordinate axes. And there's nothing wrong with thinking this way, but the idea is that we think of this as the 0 radian. We think just like we had before, pi over 2 radians. So thinking of this, if theta were just equal to 0, it would just represent this line here, the polar axis, because r would be free. And then of course we have the pi axis and the 3 pi over 2. So for instance, if we have, let's just write a coordinate pair here. Say I call this coordinate pair 2 pi over 3. So this is going to open the door to how we actually define the polar coordinate transformation. So let me just appeal to your intuition. So we would say r is a directed distance measured from the pole. Again, the origin, this is the pole right here. And this is the polar axis, which is usually what we just call the x-axis. Positive polar axis would be the positive x-axis. So these are the conventions and the terminology that we have in polar coordinates. Good or bad, it's the way it is, unfortunately. This has been set up long before we came into the picture. So now what we can do is think of that directed distance here. So we have the distance r here. And then of course, we've got this measurement of an angle from the positive polar axis here, which is pi over 3, right there. Now, of course, if you think about an equivalent representation of this point, you can use this identity. So, and to do this, we can think of adding pi. So for instance, if we have the point -2 and we add pi to this, this will give us 4 pi over 3. So using this identity, this would be a way of actually writing this particular point in a different fashion. That is an equivalent expression of this point. Now, if you think about this, what's interesting about the way we've defined things is that from 0 to 2 pi and r positive, we're going to get what we call a one-to-one transformation. For instance, if you thought about this and you said, okay, well, if I take this point or take this particular point here, and then I've got this angle, and then I've got this negative here. There's an example that we're going to do where if you look at this and compare the two, these both represent the same point. And so as long as we keep the r positive and we look from 0 to 2 pi, we can't do this, because you're seeing the only way that we can actually write an equivalent point is to jump into the negative. Now, of course, we could use this over and over, and we can just add 2 pi here and just get what, 7 pi over 3. Not very interesting, and of course, we don't even think about that. That's what we've been doing in trig all along. But now we're combining the negative, so to speak, the value, the additive inverse with the r, and getting an equivalent expression. So this is something that you'll have to think about, and also think about the reversal of direction of vectors. So this would be an equivalent. So we could just basically say these were equal in terms of the polar coordinate representations, which is using this particular setup here. Okay, so if we start with this, notice in this particular case, to get this to work out the way we want to, we would want to be able to subtract a pi in this case. So we'd have k equal to -1, and that would give us the theta in this particular case. So this might take a little bit of time to get used to, but not much. It's how we can actually infuse the directed distance into the polar coordinate system, and then give us a way to write particular curves in the plane that would be really difficult with the x's and y's that we're accustomed to. Okay, so this I wanted to just flesh out and give you an idea about. Now, let me talk a little bit, ladies and gentlemen, about this transformation setup. What you're looking at this and saying, well, Professor Ron, that's a triangle, that's a right triangle. So let me go ahead and give the transformation that we're dealing with. What is it? Transformation. So, for instance, you're thinking, we've got this polar coordinate system, and you've drawn what appears to be a right triangle here, or at least you've implied one. So how would we have a transformation that would take us between the actual Cartesian coordinates and the polar coordinates? And I'm going to write that down for you. We'll just call it T. I use this a lot in Calculus 3. So we're going to go from the plane to the plane, defined by. So we'll have T, and this is my notation, operating on, using the lazy notation. Of course, we should use brackets, but we don't. T operating on the polar coordinate pair r theta. And this will just equal the following coordinate pair, r cosine theta. And you're thinking that's trigonometry, r sine theta. Or of course, this will just be the x and the y coordinates. So if we looked at this, we're thinking, okay, well, that 2 is just r times the cosine of pi over 3. And then, of course, the y would be r times the sine of pi over 3. So the idea here is that this is something you've already done. We've just added another way of framing this and called it a new coordinate system. And you're thinking, well, why? Well, someone thought about this and it turned out to be a very, very useful consideration. So now what I want to do is say a little bit about this one-to-oneness that I mentioned, and I need a new sheet because I don't want to put everything at the bottom of the page and run out of room. So now, suppose theta 1 and theta 2 live, that's what I was saying before, live between 0 and 2 pi. And R1 and R2 are positive. So I was saying, if you stay in this realm, then with theta living here and R positive, we get a one-to-one setup. And so what I'm going to do is to look at the following. Now, notice when we have something of this nature here, why did I choose two of these and why did I choose two of these and think, well, what's the deal here? Well, we want to show one-to-one. So we want to show T is one-to-one for this region. When we say one-to-one, it's invertible. So what we can do is consider the following. We just want to show in this particular case that if this is true, that is, if we say T of theta 1, well, let me do it in the right order. So we're going to have this T of R1 theta 1 equals T of R2 theta 2. That would mean that R1 would have to equal R2 and theta 1 would have to equal theta 2. So we want to consider this. So we want to show one-to-one. That is R1, not necessarily in this order, and theta 1 equal theta 2. So using our polar coordinate transformation, what does this mean? Well, this means R1 cosine theta 1 equals R2 cosine theta 2. That means these would both have to be equal. So we just switch out the R1s and the R2s like we have here. And we would have R1 sine theta 1 equals R2 sine theta 2. Now, when we can do this, we can actually write down the inverse transformation. Now, notice, what does this tell us? Well, let's just work with this and see what we can get. We can get a ratio in both cases of R2 over R1. And again, we're not dividing by 0. No need to do that. That wouldn't be very useful, right? So here, if we divide, that is now we divide by R1 here, and then we have cosine theta 1 over cosine theta 2. Just do cross multiplication. So again, divide by R1, divide by cosine theta 2, and we get this. And let's do the same here. This is just my proof of this. It's easy and it doesn't require anything fancy, just basic trigonometry. I come up with a lot of proofs when I'm doing my own work, trying to come up with ways to validate things for the courses I teach that don't go outside of what you know. Otherwise, they wouldn't make any sense. So now, notice if we set this up, that means these two ratios of the sines and the cosines will be equal. So we can set these equal. I tell my pre-cal students that this is what you do in calculus, so they better get busy understanding the trigonometry. So now if you look at this, we're thinking, okay, well, this is starting to look like an addition formula or a subtraction formula. So we can multiply this out. So let's cross multiply. So we'll have cosine theta 1. And of course, Professor Ron always likes to put the sign first. So I'm going to put the sign first. And then here we can cross multiply. Because when I write my identities in pre-cal, I like to do this. So again, sine of theta 2 times cosine theta 1 equals sine of theta 1 times cosine theta 2. And now, of course, let's just put everything on one side. Let's take this over here. So we have sine theta 1 cosine theta 2 minus, bring this over, and then take the mirror image, sine theta 2 cosine theta 1. This equals 0. So now, of course, if you look at this, and I know you're thinking, well, Professor Ron, that's just the subtraction formula for sine. So this is just subtraction formula, which you learned in pre-cal. One of the most important formulas you learned, the 4 formulas of this nature that you learn give rise to the product to sum and the sum to product, which we have used heavily in this class, or at least when we were doing trig integrals. And they're very important. And those of you that go on to do Fourier analysis will continue to use these. So now we get sine of theta 1 minus sine, or minus theta 2, of course, equals 0. Now, this is really the most important part. In this part, at this point, it's pretty simple. And of course, this is what confounds every trig student, especially when you end up on the axis. They want to get all fancy and use Professor Ron's lemma. But now notice, if this is true, if we look for all particular solutions, this would just be when theta 1 minus theta 2 would be on the x-axis, just thinking as a multiple of pi. So this says theta 1 minus theta 2. I tried to make this as straightforward as I could, and I rewrote this a couple of times. Again, like right along the axis, 0, pi, 2 pi, 3 pi, etc., negative 5 pi, things like that, right on the x-axis. So now, if you look at this, and this is important, we can now think about how we can actually write this. That is, if and only if theta 1 equals theta 2 plus k pi. So now let's check these out. Let's look at k equals 0. When k is equal to 0, we just have theta 1 equals theta 2, and that's really what we are looking to hope makes sense in this case. Now, for k equal 1, and I've written these two cases here. Let's see, what do we get? So we've got theta 1 equals theta 2 plus pi. Now, let's just see what this says, and this is where we don't have to go much past this, and if we did, it wouldn't work, right? So now if we look at this and say, okay, what's the deal here? If we think about our hypothesis here, we've got two cases here. That is, notice this can either be, since this is pi, in the 3rd quadrant or the 4th quadrant. So what does this imply? And I've written this out fairly clearly here. Theta 2 plus pi would be in the 3rd quadrant, or theta 2 plus pi would be in the 4th quadrant. Now, of course, if theta 2 plus pi is in the 3rd quadrant, this means theta 2 must be in the 1st quadrant. And then, of course, if theta 2 plus pi is in the 4th quadrant, this would say that theta 2 was in the 2nd quadrant. Now, Now notice, and this is kind of an interesting situation here. When we think about this and we say, okay, well, would this be something that would make sense? Now notice, if we have a setup for this particular case here, and notice that the difference that these two, well, excuse me, these two angles live again in here. So we're thinking, okay, theta 1 and theta 2 live here. Now, noticing in this particular case, what would have to be the case if theta 1 equals theta 2? That would mean that they could live anywhere from between 0 and 2 pi, and we're fine. And this would have to be true. Of course, sine of 0 is 0. And now, of course, if things are separated by pi, then is that going to also give us something that will make sense? Now, notice, and this is important, if you think of theta 1 and theta 2 as far as where they actually live, notice here that we have this separation right here. So if theta 2 is in the first quadrant, theta 1 would have to be what? In the third. So let me just go ahead and write this in. And then we look at this and say, okay, well, does this make sense? Well, if theta 1 is in the third quadrant and theta 2 is in the first quadrant, how do the signs compare? Well, they could never be equal. That is, note, sine is greater than 0 for quadrants 1 and 2. Sine is less than 0 for quadrants 3 and 4. So this would make an impossibility. That is, we could not have these signs coinciding because the actual plus and minus would not be consistent. So this implies impossible. So we don't have to go any further because it would only get worse. So this means that where we started, theta 1 must equal theta 2. And then I said I needed an extra page. I need an extra 2 pages. Then we can go back to our equations at the outset, which will finish everything off. Now we know theta 1 equals theta 2. Then R2, just pick one of them, over R1 is cosine of theta 1 over cosine of theta 2. So this equals 1. If and only if R2 equals R1. And that's what we wanted to show. So T is 1-to-1 for R positive and theta living between 0 and 2 pi. Now, this argument may be a little bit long-winded, but it's simple and it only uses ideas that you learned in trigonometry. Nothing fancy, I mean, we didn't even have to use any calculus here, which we could have used. So now what you're seeing here is what we thought was the case all along, which is that if you restrict to this particular region, then the transformation is 1-to-1. And so we can actually think about an inverse T. So what is the inverse map? That is, if it's 1-to-1, T inverse exists. At least we can write something down that will help us to move forward. So how do we do that? Well, we're just going to be cheap and use what we know about trigonometry. And this is kind of funny. So what is T? Let's figure it out. Well, x squared plus y squared will be r squared cosine squared, like I was doing last week when we were working with the hypocycloid, and I didn't apply the 1/3 first, so that when you squared, I said, I know this works, and I verified it with my integral, but it's very simple to leave out something very straightforward when you're thinking it's harder than it is. But my intuition told me this has got to be correct, and our integral verified that. So when we look at this, we get r squared sine squared. But of course, we can factor the r squared. And of course, that's just the fundamental identity, which is 1. So this is just r squared. So when we look at this and we're thinking, you know, the way we've looked at this here, again, I keep going back to this. We've got this set up here with the r and the theta. And so now we will select the positive, because remember, for our one-to-oneness, we were assuming this. Even though r can be directed and have values less than 0, this was our hypothesis to prove the one-to-oneness. So this implies that we can select the positive square root, and so r would just be the positive square root of x squared plus y squared, which is what you think it should be from trigonometry. So that's no surprise. So this is what you expect. But it should be consistent, what you expect. And then now, of course, so this is helping us to find the inverse transformation. And then again, we can be cheap again because we know trigonometry. So we'll say observe. I should have said observe here, observe. I used to have a student that could say the observe really well, and I'd always point at him in class and say, what's the next word? And it always got a chuckle in class. Whatever. It was funnier for the student to say it than Professor Ron. So now we can just look at y over x, which will be r sine theta, r cosine theta. And of course, this is sine over cosine, the r's absorbed, and we get tangent theta. But then equivalently, we have the one-to-oneness. So theta can be defined as the inverse tangent of y over x. Now, of course, that will give us a region from negative pi over 2 to pi over 2. And of course, we can mod out by pi if we need to push things around. So remember, this lives, we did this back at the very beginning of the class when we were doing the derivatives of the inverse trig functions. So again, you do hyperbolic inverse in Cal 1, then you get to Cal 2 and get back to the regular trig functions to do this. So at least we have formulas. We don't always get formulas. So now we can say T inverse such that R2 maps into R2 defined by, so we have T. Now, again, we've got what XY going in the reverse direction will be square root x squared plus y squared, and then inverse tangent of y over x. But of course, this just equals r theta. So before, in the previous one, remember, we had T of r theta to give us xy, r cosine theta, r sine theta. And the inverse map, of course, starting in the xy plane, going to the r theta plane, will give you this. And you'll do this, ladies and gentlemen, in Calculus 3 especially when you do the change of variable for double integrals. This is a linchpin. You have to be able to write down the inverse map and then know the connections between them, at least in terms of determinants too. So calculus 3 is it gets a bad rap, but it's one of the most important classes you do because it unifies everything into the second and third dimensions, especially you physics gurus that enjoy physics, you'll certainly use your calculus 3. So at least we know we have something that Professor Ron just didn't make up. Okay, so this is real. This is not just a bunch of fluff. Okay, so let's do some exercises with this and then talk about some graphs so we can use our nice handy chart. So for instance, here's a WebAssign problem. We've got this Cartesian point, -8, -8√3. And then of course, the X and the Y are both negative. So again, this is Cartesian. Now, sometimes WebAssign will use the same or a synonymous term for Cartesian will be rectangular. I don't really like that as much, but I guess it's all right. Rectangular coordinates, you know, the X's and the Y's, but Cartesian is often used too. And of course, these are both negative, so this is in the third quadrant. So what it says is compute, and I'm gonna say it this way: compute the unique point in polar coordinates for r positive and theta between 0 and 2 pi. I read the WebAssign problems, and then I said they're using the one-to-oneness, so this helped me to redefine a proof for this. I've done it several different ways, but I read the problem in WebAssign, and I said this kind of opens the door to a newer proof, and then determine an equivalent point. So WebAssign's always formatting things. An equivalent point for, in this case, r less than 0, and theta between 0, 2 pi. So like I was saying before, if we start here, in order to get an equivalent point, we're going to have to go outside of this region. We're going to have to go to r negative. So this is what kind of set up a basis for the proof that I did. Here, we're not going to find another one. We're going to have to change up the r region in order to find one. So now, of course, and this is the easy part. Notice we've got these nice numbers here that the unit circle likes. So of course, this is x and this is y. So let's just look at some easy ratios. So we're going to have y over x equals -8 √3 divided by -8, which is √3. Okay, so this equals the inverse tangent of, well, actually this equals the tangent, sorry, not the inverse tangent. So we know y over x is tangent. And so equivalently, theta is the inverse tangent of √3. Now, of course, that's when the sine is √3 over 2, so that gives us pi over 3. But this is in the what? This is in the first quadrant. So we're going to have to use what we know about trigonometry to put this in the correct quadrant. But note, equivalently, pi over 3 is congruent to pi over 3 plus pi. So we can just move it around. We know that this tangent function is 1-to-1 on the interval of length pi. So this is just 4 pi over 3, which is in the third quadrant. So that's what we need. So again, the inverse trig function gives us something that lives here in the first or the fourth quadrant. And then of course we have to mod out in order to find the correct quadrant for this particular problem. And now we're good to go. So what do we have? Well, let's just be lazy and not work too hard. So we have x squared. So we have r squared is x squared plus y squared. So this will be a negative 8 squared plus a negative 8 root 3 squared. So that'll just give us what? That'll give us, in this case, a 6. Well, we got a negative 8 squared in both, so that's a 64. And then that gives us a 1 plus a 3. So this is just going to be 64 times 4. Well, that's a perfect square. So this implies that r, well, we get the square root of 64, which is 8, and the square root of 4, which is 2. That gives us a 16. Okay, so this implies the polar coordinate, apolar coordinate equivalent of this Cartesian point looks like this. So we've got what? 16 comma 4 pi over 3. So that would be an equivalent point. Now, of course, when we think about getting another point that will do the same thing, is we have to look into the negative realm. So what we can do is think about doing the addition of pi or the subtraction of pi. Notice in this case, if we add pi, that's going to be, in this case, 7 pi over 3. That's going to be too big. That's not going to be in here. So what we're going to do is subtract the pi to still keep us in 0 to 2 pi. So we want to respect, and I say this all the time in pre-cal and even in this class, we have to respect this, and we also have to respect this. So then we can say, note that 4 pi over 3 minus pi, just doing a multiple of pi, an odd multiple that is in this particular case, pi over 3. And that still lives between 0 and 2 pi. So an equivalent point, again, we'll just shoot through the origin. An equivalent point is, so we'll have negative 16 pi over 3. So again, like thinking about a vector reversing direction, this will also give us an equivalence of this, which gives us this, again, Cartesian, polar. Now, and again, this is in the third quadrant. So that's what I was talking about. The WebAssign is a marvelous tool. The thing is that the problems are set up and formatted in a way that force you to understand what Professor Ron is talking about. That's why I like the WebAssign. It's great for pre-cal too, and it's somewhat frustrating, but there is a reason to the madness. And I tell the representative Sibel Beckham at Cengage all the time when I've made suggestions and rewritten things to offer suggestions for the WebAssign. Like I say, I've known these people for 11 years, and the lady I worked with for the longest time basically instituted a lot of the recommendations that I had, and the WebAssign has just become better and better. So it's a great tool. Though frustrating, it is a great tool. So now what we can see is that we have two equivalent representations of this Cartesian point in the polar coordinate system. Now let's look at some other examples. Let's just talk about some graphs. Now, if you go over to your sheet here, we've got some circles and what we call lemniscates. And so we'll start here and then we'll do some examples of these. But you've got circles that are on the polar axis, positive polar axis, and also on the axis theta equal pi over 2. And let's talk about those. Now, what Dr. Larson says many times is that he says that the curve is easier in polar, or it may be easier in Cartesian. We have to decide. But of course, now what we want to do is focus on the fact that the polar can be very simple and be very useful to us as we work through these problems. Being a tall person and sitting at a desk has been the biggest adjustment for me with the COVID, but I'll be fine. So now let's look at an example. We have R equals A cosine theta. And we'll fill in some details here, a specific particular R, if you like, to later on when we do some examples in the next section. So what we're going to assume here is that A is positive. Now, this will be a circle. It's actually, we're going to verify that this is a circle on the positive polar axis. So the idea is that this may be useful doing a physics problem. Maybe it's simpler to stay in polar coordinates or an engineering problem. And you'd say, well, why is this true? So why? Well, first, what we can do is look at the fact that R is just R, so we'll just leave that alone. A, and note, we know that X equals R cosine theta. Of course, you could switch this out with a sign and get another circle. It's symmetric. And so we have cosine theta will just be X over R right here. So we can substitute X over R. And I'm trying to do this in a way that's simple to keep the arithmetic and the algebra easy because we don't want to work too hard, right? So now we have R times R. So this is going to be an R squared equals A times X. Now, of course, R squared is just X squared plus Y squared. Now you're thinking we're doing all this work. Why are we doing this? Well, I just want you to believe that this is true. In other cases, we'll just have a Cartesian, a polar curve, and we'll just sketch it using the Cartesian graph and be done with it and not worry about doing this. But this is a good example of showing how you can take the polar equation and convert it into Cartesian or vice versa. So that's something that WebAssign will ask you to do. And this may be something you have to do in your science classes. So here we have equals AX. And so now, of course, you're thinking we can just complete the square. So we'll have X squared minus AX plus Y squared equals 0. Now, of course, if you look at this and say, well, we can complete the square, let me just, you can, when I teach pre-cal, I usually have them put everything on one side, but we've got a simple equation here. We can take half of this, which will give us negative A over 2, and then square it. So this will be A squared over 4. And let's just do the same thing here. So this allows us to complete the square. This is monic half of this and square it. Again, what we do when we do integration. So now this will just give us X minus A over 2 quantity squared plus Y squared equals A squared over 4. But if you like, this is just A over 2 quantity squared. So we get a center of A over 2 comma 0. So we get a circle of center A over 2 comma 0. So that's on the x-axis and the positive x-axis since A is positive. And we've got a radius of A over 2. So when you look at this is just a good place to start because this is a curve you know a lot about. So now notice we can just mark off here and then just go A over 2, A over 2, and then A over 2, and just draw the circle. And of course, when you want to find where curves actually intersect, of course, it's not always going to be unique solutions, but it allows you to figure out things. You know, we have these arc length formulas that we learned last time in 10.3, and the area, surface area, doing the parametric Cartesian derivative, you know, y prime over x prime. So that turned out to be very useful and gave us some new formulas from the old. So now notice you have the a over 2 comma 0. There's your center. And then this is what the chart, they just want to show you that the distance through the circle is just a over 2 plus 8. I like how they write this chart. It's very useful. And so if you go all the way over, which is the diameter, you get the distance a. So notice, like I said before, this is a very useful interpretation of polar coordinates to give a circle on the positive polar axis, so to speak. Likewise, so now you see what I'm talking about. And I'll say likewise, we can do r equal a sine theta with the same derivation. Is a circle on theta equal pi over 2 axis. And with the same setup here, and we will have center, the same analysis. Now the completing of the square will be in the y coordinate, just like I've done here. It's exactly the same. You should work through it, but it's exactly the same as this. So I don't think I need to do it again. This will give us 0 a over 2 as the center, and the radius, again, will be a over 2. So we can draw a picture of this. So again, go ahead and mark this off. We'll do a over 2, a over 2. Of course, this is the pi over 2 axis, a over 2, a over 2. So there's a nice circle again, 0 comma a over 2 as the center. And then of course the diameter here is a. So this is a convenient way. You can think of intersecting these circles and finding the area of the lune, so to speak. That'll be an example that we'll do next class. But first we need to know that these are circles. And so very, very simple equations here. Very, very simple equations. Now, what we might want to do is look at an example that utilizes this, but maybe takes a little bit more work. And this is where we're going to focus on the Cartesian equation. So here, nice simple polar equations for circles on the positive polar axis, and then on the positive theta equal pi over 2 axis. Okay, so some students say, oh, you want an x-axis, you want an x-axis circle, a cosine theta, r equal a cosine theta. You want a y-axis circle, r equal a sine theta, again, where a is positive. Now, of course, you're thinking with all of this that when we say r equal 1, that's just the unit circle because theta is free, it just wraps around. And then you could say r equal negative 1, that would still be true, but a little bit awkward. So we don't normally use that convention, but we can see now that lines can be represented by just values, constant values of theta, where r is free, and circles can be represented by constant values of r, where theta is free. So that in and of itself is very simple. Now, the next one that we want to talk about is right here. It's called the figure 8. These are called the lemniscates. And I'll show you how we can graph this for cheap. We don't plot points. We plot a few, but we use the Cartesian graph to get the polar graph. So here's an example of the figure 8, and it's called the lemniscate. Lemniscate. Sometimes called the figure 8. Figure 8. Now, it's not, we end up getting two curves here, and we're just going to focus on the positive for simplicity. So in this particular case, it says this is how WebAssign writes it. WebAssign's kind of crafty here. They say convert to polar form and sketch. So this is where you can look at the Cartesian form and say, well, this is kind of ridiculous. This would be hard to work out with the X's and the Y's. So we have something like this. So convert to polar and graph. So I'm going to give you a trick or a technique that I used as an undergraduate. And then, of course, when I got to grad school, I continued to use it. So again, when you look at your chart here, you've got the r squared equals a squared sine 2 theta, giving you this disposition. We're going to look, this one's going to turn out to be what we get here, r squared equal a squared cosine 2 theta. So we're going to have a trig function of a double angle. Okay, so more trig identities. So when you look at this is just r squared squared. And now, of course, well, let me not push everything over yet. And then we've got minus 3. And then, of course, x squared, remember, x equal r cosine theta. I don't usually worry so much. I shouldn't probably write these down. You know these from trig, but just to make sure we're all on the same page. So now x squared will be r squared cosine squared minus r squared sine squared. And this equals 0. So now we've got r squared squared minus, and of course now we can factor the r squared here. So we have 3r squared cosine squared minus sine squared equals 0. Now, of course, if you want to factor this, we can factor the r squared. That'll just be r equals 0, which is not very interesting. So we have r squared, and we have r squared minus 3 cosine squared theta minus sine squared theta. But of course, that's, we know we have an identity here, the cosine of the double angle. This is the cosine of the double angle. And sometimes, of course, we use 2 cosine squared minus 1 and 1 minus 2 sine squared. So this is cosine of the double angle. You know, the double angle formulas we don't forget because we actually use. So if and only if r squared equals 0, or, which isn't very interesting, okay, I mean, that's not really going to give us a figure 8, but this will, or r squared minus 3 cosine 2 theta equals 0. So we'll just say good, but not interesting, not interesting. I mean, that just gives us the pole, and fine for the pole. You know, theta can be anything, but you're just sitting there buzzing around at the pole, just a point, not very interesting. So not to discount it, but it's not the figure 8. This one is more interesting. So this is the interesting curve. And this has the form that you see in your chart, the interesting form. So in order to actually use a Cartesian graph, we think of just thinking of this as the following. That is, we have r squared equals 3 cosine 2 theta. And then, of course, that gives us two, in terms of the values of R, that gives us two radicals, a plus and a minus. So equivalently, we have R is equal to the square root. So we'll just say, let me just write one square root instead of applying it to both. Square root 3 cosine 2 theta, or R is the negative radical. So we get two curves. But the thing is that the representation is synonymous. So we don't have to worry about, it just is the curve is covered in a different direction. So the one we want to focus on is this one. So again, when you look in your chart, ladies and gentlemen, you see this. You see R squared, A squared, of course. If that's A squared, then A is square root of 3. So we're thinking here A is square root of 3, like we're doing integrals. Cosine 2 theta. So that's this one, like I said before, right here, the lemniscate. And so what we can do is think of graphing this, and then just when we think of R's, we'll square root and think square root 3 and use the thetas to sketch the polar graph. So here's how we do it. Now we can just look at R squared and just focus on the parts that are on the axis and above, the negatives corresponding to this one, which we won't worry about. So now when you look at this, notice the period has been cut in half. So it's only, in this case, pi. So let's just draw, a little bit of this. I think, and it doesn't matter. Sometimes you think, well, how much do I have to draw to get the curve? If the curve is closed, you just draw until you close the curve, or you get a curve that starts to repeat. So now, of course, we have 0. So of course we do pi. So we divide that by 4. So that's pi over 4. And then 2 pi over 4, which is pi over 2. 3 pi over 4. And then pi. Then 5 pi over 4. 6 pi over 4. 7 pi over 4, etc. Just write out several so we can do the principal values like we did in trig. Okay, now, if you like, if we think about this, if we just graph R squared, we just have a 3 up here, and then when we take the square root of it, that'll give us a square root of 3. So we can think of it this way, 3. And then we've got the cosine. So we've got what? The 3. So we get the 1, the 0, -1, etc. So just kind of bump through. Just like you do in we're not doing all the transformations because, as I tell my students, you're good at this now. So when we look at this, let's go ahead and draw this. Let me position the paper this way so I get a better looking graph. Now below. So these are like I guess I can just kind of dot this because we're not really as interested in this. And then of course this part. And I'll just go 1 over 1 more. 8 pi over 4, which is 2 pi, which is up here. So now what we can do is look at these as the values of the R, but now we're going to square root this, and so we'll have values, positive R values. So we're only going to focus on the part that's positive here, since we're looking at R squared. So now when we draw this, let's just draw our polar axes. Think of this as Cartesian if you like. And this one has issues at the pole. It doesn't have the derivatives don't exist because it just gets a little wonky. You know, it's not smooth. So when we look at this, we start out again, we want the actual figure 8. So the r here will be square root of 3. So I can mark this off as square root 3. We'll start out with that. And then notice here we got square root 3, the square root of this at 0. And then we've got this pi over 4. So let's go ahead and mark off pi over 4. And then, of course, notice when we get to a 0 here, we're at 3 pi over 4, which we can mark off too. Make sure I got eyeball that about right there, I guess. So this is the cheap way to do it without having to plot a million points, which would never work anyway. So theta equals pi over 4. Theta equals 3 pi over 4. And so now when we r becomes 0 here, so as theta moves from 0 to pi over 4, we get a value of r equal to 0 here. So our curve will look something like this. It'll be part of the loop. Right there, at the angle pi over 4 at 0, right there. So there's an r value of 0. Here's an r value, r squared value of 3, or an r value of square root of 3. And then here, this is no man's land. We're not interested in that because that's not the curve that we're looking at. We're looking at this one. So this doesn't give us any addition to the curve. Now, this is what I was talking about. At 3 pi over 4, we don't just smoothly come back around here. We just kind of have a jolt, and then we move up this way to here and 0 out at pi. So here at pi, this is pi. So theta equal pi, and this of course is theta equal pi over 2. We're back at 0 here, but now we have a jerk in the curve and go this way, 3 pi over 4. So we're slanting up here and moving around, getting smaller and smaller value of r back to 0 here. So again, symmetric, even though my curve doesn't look like Rembrandt. But now, then we've got the phi. As we go to pi here, we're going to slide into 5 pi over 4, which is what this is, theta equal 5 pi over 4. But slide back into 0. So here. Like that. Now, of course, I can make this look a little bit more robust here to match what I have over here. So it looks a little better. There we go. And then no man's land, but then we have another jolt and move to 7 pi over 4. So again, we've got a nice kink here, but then we move all the way to here, we're at 0, and then back to 2 pi to complete the figure 8. Right there. So the idea is that the tangents at the pole don't exist. That's like wasteland. I mean, you're driving along and then you get this big old jolt and you don't change direction smoothly. But if you see here, we're not interested in this part because we're looking at the positive square root here. And the idea is that if we wanted to dress the curve using these, we would get the same curve. It'd just be a little bit harder to negotiate the negatives. But we'll have some negatives, values of r, which we'll work with. But But you see now that this, though it does describe implicitly a figure eight, this curve is easier in this form. So we look at the implicit curve here, which is what you see in your chart, and then you say this implicitly defines the figure eight. That's easier. You can look at this and go from here to here easily. Here to here would not be simple at all. So the polar curve here is the valued curve, so to speak, is the curve that we approve of in the sense of simplicity. So when you think of a strategy in mathematics, you're thinking, well, let's go with the strategy that's simpler to write and simpler to understand. So this is what Dr. Larson was talking about. It's like in the polar form, it's easy to see that this polar curve is the figure eight. And like I say, we cheat with the Cartesian curve from pre-cal to get a value of the thetas and a value of the r's and use this as a guide to draw this. So this is a invaluable tool, Cartesian graph to draw the polar graph. And that's how you do it. Otherwise, you just plot a bunch of points which would go nowhere. So we use Cartesian graph to get the polar graph. So that's the key here, and that's what makes all of this actually work. Okay, so I thought that was kind of neat. Now let's look at another example where we do exactly the same thing. You don't have to guess at this. And then of course, if you have your chart, you already kind of know what it's going to be like, and that gives you a step up without having to start completely over. So now let's look at an example. Let's do a rose curve. These are fun. So the rose curve, again, in your chart, you got the rose curves. Again, these are like petals of a rose, so to speak. And here's some easy examples. And these have very simple polar equations, just like the figure eight have simple polar equations. So let's look at an example. So in this case, we've got, let's see here. Okay, I'll do kind of the like with the circles before, give you the polar equivalence. The rose curves can easily be seen with the Cartesian graph. And here's what we have. We have R equal A cosine of the multiple angle in theta, and you can use a K or an N. The chart uses an N. I like Ks, but substitute whichever letter you like. Again, we'll take N to be an integer, just like the K. And then we have R equal A sine in theta. Again, I'll do this so it's clear. Of the multiple angle. And here's the deal. This just comes directly from the Cartesian graph. If N is odd, say N is 2K plus 1, that is odd, this will imply, I guess it's good we're using N, now I can use K. This will imply N petals. So with the petal, it's like doing the figure eight. You've got to start out to get one side, and by symmetry, you get the other. So that's two pieces of a Cartesian graph that you have to create the closed petal loop. So yeah, you can see how the Cartesian is very useful. Now, by the trigonometry, if N is actually an even number, even in the sense of divisible by 2, this will give us 2 N petals. So we get twice the number of petals we would get if we were using the odd argument, so to speak. So let's look at an example of this. Here's a nice simple example. R equal 5 cosine 2 theta. I wanted to focus on at least the ones where we have the double angles so you can get used to that. Just to remind you a little bit about your trigonometry. you know, it gets rusty really fast. And we haven't done a lot of graphs, but you all are good students, so you'll be okay. But now we see that we have the form here. So if you see this in your WebAssign, it's like, oh, that's a rose curve. That's a rose curve, and that already gives you a leg up. Now, just like we had before, the period here is going to be 2 pi is going to be divided by 2. So that's going to give us a period of pi. So let's just draw the Cartesian equivalent and use the Cartesian to get the polar curve. Now, remember, we don't have any squares here, so we won't have to work as hard. So we'll just do a simple Cartesian graph. Let me get a better line here. All right. This is not vertically shifted, so we don't have to work too hard. So now we can mark off 5, just any scale you like, just so that we know that the maximum in this case is 5, because we've got a cosine function. So we have pi over 4. We'll just get the principal points. 2 pi over 4, pi over 2, 3 pi over 4, then 4 pi over 4, and then 5 pi over 4. I'll do the same as I did for the last one. And then 6 pi over 4, which is 3 pi over 2, and then 7 pi over 4, and then 8 pi over 4, which is 2 pi. You know, when you teach your pre-cal kids, you tell them to keep the same denominator so they don't go crazy with trying to get common denominators. This way you can space things out and you get a nice, neat graph. So now with the cosine, just like we had before, we got the 5, the 0, the negative. So we're going to have some negative values of r. We have the 0, and then back to the 5, and then the 0, the negative 5, the 0, and then back to the 5, just to get a couple of periods there. So we can draw the Cartesian graph. Again, this doesn't have to be a work of art. This is just a quick sketch. Again, the Cartesian technique is the way to go. It gives you all the information about the thetas and the r's in a way that you can understand. So again, we're thinking of theta as independent as r is dependent. And of course, when we do our Cartesian derivative, we'll go right back to this and see that it meshes with the dy dx that we proved last class, remember, with the chain rule. So that simple formula already innervates the polar coordinate transformation. Why? Because I've already taught you what the transformation is, you know, r cosine theta, r sine theta. So that will open the door to the Cartesian derivative for us. So now what we can see here, look, we've got values here. I'll just go ahead and mark in some r's. Here's an r, here's an r here, the maximum value of r, so to speak, maximum value of r. So all over the place, we've got these r's. And then we got where there's zeros, and then when they change sign, and then we do the reflection through the origin. So now let's just go ahead and draw a polar axis with a pi over 2 axis. You always have to spend, the way I set up this schedule, I set it up so we have enough time to talk about this. You can't, you got to spend time on the more difficult things. And this is not overly difficult, it's just new. So that makes it, you know, take a little bit of time to talk about it. So here's our pi over 2, here's our pi, and our 3 pi over 2. Of course, theta equals that, and I'll just kind of shorthand that a little bit. And let's go ahead. The focus has been pretty good today. Okay, now focus, double entendre, right? Okay, so now now we're thinking, all right, so we've got this positive value here of 5. So let me shift this so you can see this. So now we start out at 0. So here are all the values of 0 or theta. We start out at 0 and we're at 5. We can mark that off. And notice we hit, again, we've got these pi over 4. So let's go ahead and mark all of this off. We got 5, 5, again, not Rembrandt, but maybe quasi Rembrandt. So we can go ahead and mark off all of these nice pi over 4, 3 pi over 4, things like that. Mark off the ones that we think we're going to need to use just by looking at this graph. So here's the pi over 4, 3 pi over 4. We've got the 5 pi over 4 and the 7 pi over 4. So now you can see here, we start here, slope back around to 0 at this angle. So let's just kind of fill that in. Again, we're not applying so much calculus here as we're just applying the fact that we've got smooth curves. At least we'll see that they're smooth. In this case, we get nice smoothness at the origin, which we didn't get with the figure 8. Now notice we have the situation here where we have a 0 at pi over 4 here, but then notice we go into the negative realm. So this is a pi over 2, but r is negative. So that shoots us through the origin. So this point here is shot through the origin to here. And so again, with the negative values using the identity, reversing the direction of the vector, and notice we come around and then we hit down here at the 0. So that tells us exactly what to draw. Reflecting, not going up here, but being nice and smooth and ending up down here. Right there. And then as we move there, we're not at 3 pi over 4, but we're reflecting through the origin. So we end up at 0 right here. Again, we're not over here, we're reflecting through the origin. And then we get a nice pi over 4 angle. Right there. Now at this point, we're back into the positive realm and we have to hit the pi at a value of 5 here. So we've got the 5 here. We have to hit the pi there. Again, maintaining the angle at the pole of 3 pi over 4 and then hitting the pi. So smooth, nice and smooth. We don't have a jerk in the direction. And now, of course, we come back down with the value of R decreases back down to 0 as we slide right into 5 pi over 4. So you can see that this technique is valuable and why we select it over plotting points. Slide in right at pi over 4, 5 pi over 4 right there. And then, of course, as we move here, this is, again, negative 3 pi over 2, we shoot through the origin. That is, if this were positive, we'd be here, but then we shoot through the origin and we maintain an angle here that's nice and smooth to take us up to pi over 2 because the value of r here is negative 5. So we shoot through the origin, just like vectors. And then we level out. And then we're thinking we're doing the same thing. We want to end up not at 7 pi over 4, 0, but shot through the origin at 3 pi over 4 and come back down. It's not very symmetric. come in here for a landing at, again, 7 pi over 4. And then we finish off at 5 when we come right back around to 2 pi, nice and smoothly. Okay. Now, of course, my curve looks terrible. These should all look congruent as far as curves, but, you know, freehanding it, we still get a nice rose curve of 4 petals. So again, 2 theta, 2 is even, so this implies 4 petals. Remember, when we have n is even, we get 2 n petals. So again, n equals 2 implies 2 times 2 petals. Okay? Now this is simple. You could learn how to do this in pre-cal, but it's a little bit advanced because you've got to really know some trig. And if you just learn trig, this might be kind of hard. And then you're just plotting a bunch of points. And of course, that's absolutely useless. So this Cartesian graph gives you the value of the theta. And with the identity with the negative r's, it shows you how to shoot through the origin to draw your graph. And notice nice smooth issues at the pole. We're not jerking the direction, you know, pi over 4, then we switch to 3 pi over 4. It's a nice smooth transition here that we don't have with the lemniscate. Now, there's an example that I want to talk about, and I keep talking about the poles and stuff. So, and the Cartesian derivative. So let's just look at, you know, what might be the case here, like if we were really interested in a Cartesian derivative. Because when you look at what we have here, it looks like we've got some horizontal tangents, we've got some vertical tangents, you know, we've got some nice things going on here, but it doesn't appear to have any cusps, which is good. You know, with the lemniscate, you've got all those issues at the origin because you're getting this going on, which is a jerk, which is not a smooth transition. So it's like when you talk about a curve being piecewise smooth, it certainly has that. But this is nice and smooth. This is really nice curve here. And of course, you know, we have infinite tangents here, but at least one of the derivatives, when we do y prime over x prime, we know x prime is 0, but y prime isn't. That's why we get a nice smooth transition, even though it's a vertical tangent, it's not a cusp or a corner. Now, so how do we get the Cartesian derivative? So let's talk about that. Now, there's an example here in your WebAssign that talks about using the actual Cartesian derivative. And they say, compute slopes of the tangent line at the following points. But, ladies and gentlemen, the points aren't given in terms of the Cartesian, they're given in the polar. So we need to come up with the dy dx with the polar. So here's the Cartesian derivative. So when you have parametric representations, which we have now, we know what x and y are, we have to use our theorem about the Cartesian derivative. So in this case, we will suppose, how's this going to work? We're going to suppose r is a function of theta. Okay, r is a function of theta, just like we have f is a function of x. Okay, and we know we have the invertibility because we know to prove that we had to have some invertibility, which I painfully tried to show at the beginning of the lecture. Not painfully, but I mean, we had to do some trig to get it to work. So now we want to suppose that r is a function of theta. So basically, let me show you how we would write this. We just say r equals r of theta, just to make that make it more clear. So we'll say differentiable function of theta. So now when we look at this, and I'll write these in the order that we have y is equal to r sine theta. I'll put the y on top since it goes goes in the numerator. If you put the x on top, you're tempted to put that in the numerator. So maybe I'll help us all out. And then of course, x is r cosine theta. And so some of what we're doing today will bleed into what we do in section 5, because the section 4 is really full of a lot of stuff. I mean, it's one of those sections where you think, well, there's not much here, but there's actually quite a bit. So when you look at this, you think, okay, well, what's the formula here? So now notice the Cartesian derivative, as we had before, will now be the ratio of the parametric derivatives. So we've got parametric. These are now, of course, now we look at the actual transformation as the parametric equations now, which we did in section 2. So these are the parametric equations. Parametric. So it's all back to that. And of course, this will be y prime of theta divided by x prime of theta. So that we proved last class before your break. Now, of course, now we can just use the product rule. So this will be r prime times sine theta plus, now we have r, and of course the derivative of sine is cosine theta. And now we have r prime cosine theta. So you don't have to memorize this formula. I mean, you could, but you can always easily write it down, so you don't have to, memorize. It's easy to write down. And then of course the derivative of cosine is the negative sign. So we get minus r sine theta. So this gives us the Cartesian derivative when we look at the polar graph, so to speak. So as we had before, we have a set of parametric equations, and now we recoup, so to speak, the Cartesian derivative. And so Cartesian derivative of parametric equations in polar form. I mean, before we didn't really talk about the parametric equations having a specific form. Now they have the polar form. So when they have the polar form, these are what the parametric equations are. And then we just fill in the theorem again. So nothing new here. So let's take an example of this. So say, here's a Webasine problem. Say we have the polar equation here, r of theta is 2 plus 3 sine theta. So that's our polar equation that we have here. Everything has to come together. I may be a little bit meticulous about things, and I may be more particular maybe than you're accustomed, but things have to be consistent. And if they're not, then you don't bridge the gap from not knowing to knowing. It's important to be able to see how things fit together. And so now, of course, with this derivative, we're going to need r prime. So let's go ahead and write this down, r prime, and then we can come up with a nice form of this. This will be what, 0, so this will be 3 cosine theta, if you like. Now, and what we want to do is the following. So we're gonna work with this, but the Webasine says the following. It says compute slopes of tangent lines. So I'm going to write down what we're going to do. Compute slopes of tangent lines at the following points: -1, 3 pi over 2. And of course, if we convert to this, then all we have to do is substitute the theta, because this will be independent of r. So this is indeed a function of theta. So that at least simplifies that part of it. And then we have 2 comma pi as polar coordinates. And then we have 7/2 pi over 6. So these are all points, but the only ones we're really going to have to worry about when we compute the slopes will be the values of the theta. So that should be clear. So now what does this give us? This implies that dy dx, let's just go ahead and fill everything in. We get 3 cosine theta, that's r prime, just fill in the formula, sine theta, plus 2 plus 3 sine theta times cosine theta. So again, r prime 3 cosine theta times sine theta, and then 2 plus 3 sine theta times cosine theta. Fill in the bottom, r prime 3 cosine theta times cosine theta, and then minus, so we have r 2 plus 3 sine theta times what? Sine theta. So maybe it would be to our advantage to see if we can simplify this a little bit, because it has so many thetas in it. There'd be a lot of substituting. So let's make it as simple as possible. So we get what? 3 cosine theta sine theta. Now, if you look at this, that we've got the common factor of cosine theta, and you might think, well, we can just factor it that way. But yeah, I mean that might be just the easiest way to do it. Just staring at this, yeah, let's do it. Keep it simple. So let's just go ahead and factor. So we'll get what? 3 sine theta plus, in this case, so let's see here. Then plus a 2 plus a 3 sine theta times cosine theta. So everything's got a cosine theta in it. And then downstairs, we've got a 3, so it looks like we're going to have a double angle, cosine squared theta minus 3 sine squared theta minus 2 sine theta. So now if we look in this, we can simplify this even more. So we're going to get 6 sine theta plus 2 times cosine theta. And then downstairs, of course, we're going to get the double angle again, 3 cosine squared theta. Of course, you don't have to do any of this, but that's a whole lot of substituting, and we don't want to do that. So let's opt for easier, minus 2 sine theta. And so now, of course, we have a common factor of 2 here. So we can write this as 3 sine theta plus 1 times 2 cosine theta. And then, of course, downstairs, we have the double angle. So this will be 3 cosine 2 theta. This kind of reminds us of what we were doing with the arc length last class. And remember when we took the cone out of the sphere and figured out how much surface area we removed? That was really a simple problem if you think of the parametric representation of the circle. So life is not always difficult, but we still have computation to do. So this will be our Cartesian derivative. So the idea here is to make this as simple as possible. And now what we can do is we can compute some of these derivatives here. So let's do the very first one. Let's see, what do I have here? Let's try this one first. So we can call this 1, call this 2, and call this 3. So 1, we have dy dx. In this case, where, excuse me, theta equals 3 pi over 2. Kind of forced with this unwieldy notation when we use the Leibniz, and this is standard. I guess you could put parentheses, that would be okay too. But I'm accustomed to this, and good or bad, we'll just do it this way. So we'll substitute 3 pi over 2. So we get 3 times sine 3 pi over 2 plus 2 cosine 3 pi over 2. And then we have 3, and of course this will be cosine. We hit that with a 2, that'll just be cosine of 3 pi. And this will be 2 times sine of 3 pi over 2. Again, in the denominator, the 2 absorbs the 2 here, so I just wrote the 3 pi. Now if you look at this, I left out my 1 here, and then of course the multiplication. Plus 1, all in parentheses. So here we have 3 times sine of 3 pi over 2 plus a 1. Let me write that so you can see it. Times 2 times cosine of 3 pi over 2, and then of course the denominator. Now of course here, this is just a 0, cosine of 3 pi over 2. So we just get what? Negative 1 times 3. So negative 3 plus 1, all times the 0. So that's just going to be 0 upstairs. And then downstairs, of course, we don't get 0. We get a 3 times, and then, of course, cosine of 3 pi is cosine of pi, which is a negative 1. And then we get minus. So sine of 3 pi over 2 is negative 1. So this is a negative 2 times a negative 1. So we get 0. So we've got a negative 3 plus a 2, which is 0 over negative 1, which is 0. Okay. So that, of course, we have to make sure it's defined. We don't just want to jump out, and say, because it could be a cusp. We could have indeterminate 0 over 0. So we need to make sure that we are not dividing by 0. So that's legitimate. So let's look at 2. Again, we're just doing some basic trigonometric substitution in terms of arithmetic, not the integrals. So here we've got theta equals pi. So let's substitute. So we get 3. Again, here's our recipe. Sine of pi. I remember the 1 this time. And then we have 2 cosine pi. And then downstairs we have 3 cosine, okay, 2 pi minus 2 times sine of pi. Very simple, but important. If we compute tangents, we need to make sure we have appropriate slopes. And so now we have sine of pi, we know that's 0, so that's 3 times 0 plus 1. And then we have cosine of pi, which is a negative 1. So this is 2 times a negative 1. And then downstairs, we've got cosine of 2 pi. That's just cosine of 0. So that's 3 times 1. And then, of course, sine of pi is 0. That's on the x-axis. So we have 2 times a 0. So this will give us a 1 times a negative 2 divided by 3. So that gives us a negative 2/3. Again, another legitimate slope. And let's try one more. I want you to be able to do this. The equation of the tangent line is not the difficult part. It's the computation of the derivative. So I want you to be able to do these. And lastly here, let's see, we've got the Cartesian derivative. This is number 3. Yeah, this always takes a little bit longer. I always plan for a little extra time for this because this is important stuff. This is kind of fun too. It gives you a little bit of a break from the power series. But you all are good with the power series, so I appreciate your hard work. So now we've got, let's fill it in, 3 times sine of pi over 6. Again, let me just pull this down here so you can see what I'm doing. We're just filling in the formula. Let me move the cursor over. Right here. And so we'll just fill this in, pi over 2 or pi over 6 plus 1, 2 cosine pi over 6. And then downstairs right here, 3. And let me remove Professor Ron over some. Get a nice, always good to have it nice and clean, focus. Then we have 3 cosine. Okay, we've got the 2, which will absorb a 2 into the 6, so that'll be cosine pi over 3. Minus, and lastly, 2 times sine of pi over 6. So now this gives us what? 3 times 1/2 sine of pi over 6 plus 1. And then we have 2 times cosine of pi over 6, which is root 3 over 2. And then downstairs, of course, we have 3 times 1/2 cosine of pi over 3 minus, and now we have 2 sine of pi over 6 is 1/2. So now what do we have? We've got 3/2 plus 1. Of course, the 2's absorbed. We have times the square root of 3. And then, of course, we have a 3/2 minus a 1. So this will be 5/2, 3/2 plus 2/2, right? 5/2 times the square root of 3. And then, of course, 3/2 minus 1 is 1/2. The 2's absorbed, and that gives us 5 root 3. So again, these aren't hard calculations, but again, just to remind you of your days of trigonometry when life was easier. But you know, trig can be rather disconcerting when you forget it. It's like the first time you go through it, you have a lot to remember, but it's very useful in the calculus as we've seen many times. Now, I want to do set up one more example, and then we want to do some. We'll do an example of the tangents at the pole, but I'm going to have to do a little bit more setup with that on next lecture. But I just want to give you an example of another curve. So next class, we'll do tangents at the pole. But I need to say more about that than I have time, tangents at the pole. So let's just look at another simple example of what we call a limacon. So when we talk about tangents at the pole, we're going to talk about where the tangents, where the curve crosses the pole, so to speak, the origin. And I want to say a little bit more about that. So that'll be next lecture. Next lecture, there we go. So this is what we call a limacon. Now, the limacon, that's a cedille here, cedille. Well, I guess I need to spell it liaison. Let me just write it out so you can see it. Limacon, like Lima, Peru. Limacon. There's a little cedille there, limacon. And there are several examples of this. Of course, I cover up my. We're going to do one that has a loop where the A over the B is less than 1. So you can get just kind of a squashed in circle, a dimpled circle, a cardioid, and the inner loop, okay? And these are easy to spot. R equal, and of course, we think of this as the A plus B sine theta. And in this case, A over B equals 1/2, which is less than 1. So this will give us what we call an inner loop. Inner loop. So what I thought I would do is just a real simple example of a Cartesian graph and show you how you can get a quick polar graph for free. So now notice, let's get our cheap Cartesian graph. Period's just 2 pi. And we'll draw as much as we need. So we'll do what, pi over 2 pi 3 pi over 2 2 pi 5 pi over 2, and then of course 6 pi over 2. Now notice we've got the 1 here, so everything is shifted up 1, and then everything is stretched by 2. So the biggest we're going to get is 3, right? So we have 1, 2, 3, and then we have a 1 and a 2 downstairs. So here we've got what, -1, we have 0, 1, 2, 3. So when we start out at theta equals 0, we've just got 1. And then we hit pi over 2, we have 1 plus 2, which is 3. And then pi back down to here. And then at the pi over 2, we get the 1 minus the 2, which takes us to negative. So we're going to get some negative values of r. And then we shoot back up to 1. And then, of course, 5 pi over 2 shoots us back up to 3. And then back down to 1. So this is just a simple curve where we have a vertical stretch and a vertical shift upward. So we don't do the fancy transformations you did in trig because you know how to do that. So if you just eke out a quick Cartesian graph, you can get a quick polar graph. But don't be so quick with the Cartesian graph that you come to grief. So now, if we look at this, we've got an R here, got a positive R all the way up here up to 3, then got an R here, then we hit 0 between pi and 3 pi over 2, and then we have an R here of -1, and then we have an R here of 1, we got a 0 there, and then another 3, and then a 1. So that kind of gives us a way to draw this thing, and it's not hard at all. You can see with the polar graphs that this little chart's going to be very useful. And you can practice just making up your own examples and using this Cartesian strategy that I've shown you. Plotting points is not what we want. It's too difficult, and it doesn't give you anything that you can use. This chart just acquaints you with some very popular polar forms that are easy to spot. So we're going to get a 1, radius of 1. I'll spread this out just a tad, just a little bit more. So we get a 1. Then we get a 3 at pi over 2. So 1, 2, 3. And then by symmetry, we get another 1 over here at pi. So this is like super simple so far. So we get, let me just go ahead and draw this in. By symmetry of the curve, we get this. This is fun. I mean, this is where you get to draw pictures and just enjoy yourself. Always a nice way to end a math class. That's like in Cal 3 when you end with the vector calculus theorems, but students don't like those because they're a little bit challenging. And then now notice at negative, at the 3 pi over 2, we shoot through the origin to 1. So we at pi, we die down to 0. So we have a little loop here where we die down to 0 coming this way, but not completely vertical. Then we loop up to 1 shot through the origin because of the negative value. So there's our inner loop right there. And then of course we just come back around to the 0. Again, negative. We're not out here. We shoot through the loop. We shoot through the origin to get that because of the negative value. Then we're back at 0, and then we're done. I didn't need all of this. We loop it. We close the loop here at 2 pi back down to 1. So, sorry. There you go, right there. That's it. So there's our inner loop, This is the limacon with the inner loop. And look how simple this is. See, the thing is that polar coordinates are a little bit challenging with the Cartesian derivative and then thinking about the one-to-one and all of that. But the main thing is that the polar graphs are simple because their Cartesian graphs give us a simple polar graph. The idea is that you don't even have to start with Cartesian. In these cases, you just start with the polar and you can use this as a guide. So we've got all these nice little curves here that we see are very, very efficiently represented in our new coordinate system. So polar coordinates are big time useful. And I mean, they're the prelude to the spherical coordinates and the cylindrical coordinates that you use in physics and differential geometry. So the nice thing about this is that you can use your really simple, we're not even talking about a hard trig curve, we're talking about simple pre-cal curves that you can morph into the polar curve using the values of theta and that identity when you have negative values of r when they're needed. Of course, when we do the lemniscate, we don't need the negative values because of the square root. So what we'll do, ladies and gentlemen, on Wednesday is I'll say a little bit more about the tangents at the pole, and then look how we can take some of that calculus. And now, like we did before, we're going to have a new area for area integral for polar coordinates, and then we're going to convert the actual line arc length for computing lengths of curves into the polar form, and then we're going to take the area, surface area, and convert that into the polar form. So we're going to take all the calculus from section 3 and morph it into calculus for polar coordinates. So the parametric is the same, but now that we have the actual transformation for polar, they become kind of an esteemed class of formulas just devoted to polar coordinates. You'll do the same in your physics classes for spherical. You'll do the same for cylindrical. You'll write the Laplacian in spherical and polar. I mean, you look in physics books, you flip through the end, and you'll see all of these tabulated. So this will haunt you for the rest of your days in STEM, but this will be a nice, like I say, introduction. Sorry I went a little bit over. I don't know why I apologize. I always do, but you know me. I appreciate your hanging on. So go ahead and work back through the parametric, see how this bleeds into the polar, get that work completed, and then on Wednesday, we'll try to sum everything up with the polar. And of course, maybe next Monday, it'll bleed into that lecture, and then I'll say something about the review problems that we have on the practice test. So thank you for your attendance today. I hope you're enjoying I always say I hope you're enjoying it. I hope you're enjoying the polar coordinates and our parametric equation journey. And stay warm. Like I say, we're going to have some cool weather this week. Who knows what we're going to have next week? But I will put up an announcement about the final exam. And so stay busy, keep the engine running until it's over, and then you can prop up your feet and just enjoy a little bit of time off. So thank you very much. And if I don't see you at office hours, I'll see you on Wednesday. Bye, everybody.